Wait, so how do I change it to multiple?
I don't think you have to. Okay, so for this week's homework, I think all you need is you're gonna use a single regression model, right?
Oh, yeah.
SAT score as a response, and
Mm-hmm.
the predictors should be either like expand ratio, salary takers, etc. You don't have to do a multiple, but if you try to do a multiple, I guess it's in stats. Yeah,
So this is okay, right? What I did here.
I don't think it's okay. If you click, like if in previous stage you choose a single regression model, then you can only input one predictor. I don't know what you chose in previous stage.
I didn't choose anything here. So
Yeah,
it's regression,
regression,
then best fit regression model, right?
fit regression model. Okay.
Yeah, that's it. It
Yeah,
leads to this one.
I guess you can choose four as predictors. You can choose multiple. How about you just double click on the name of those parameters? Uh,
Oh,
yeah.
yes. Yeah, it's all zero and it's the uh is this supposed to look like this?
No, it doesn't. What's your like regression formula? Can you show the regression formula? I guess it's on the top of the output. Like y equals beta 1x
Oh
beta.
yeah.
Okay, here's the problem. So first, that regression equation is right, as you can see
Mm-hmm.
it, right?
Okay.
The reason it comes out to be this kind of result is due to our rule of least square. So basically, the
Okay.
regression, like I don't know what's the precise algorithm Minitab is using, but the ultimate goal is that our sum of all the squared residuals is minimized. That's how the
Okay.
regression works. That's the least squared method. And in this case, you'll find all the residuals are zero because we precisely forecast every single data point, which is your total, by adding the verbal and math. And that is how the SAT score works, right? You just
Oh yeah.
sum up the verbal and math. By doing so, I successfully forecast all the total score without any error.
Mm-hmm.
So I didn't use the expand, the ratio, the salary, the takers. I didn't use those four parameters at all. And I only used the
Uh-huh.
verbal score and math score. By doing so, my forecast is 100% correct. My residuals are zero. So that's why you don't want to do a multiple regression in this case.
Okay.
Because you want to do some research on what's the relationship between people's expand and people's SAT score. So So by doing so, you do a single regression on expand and the total SAT score. Maybe you want to do like a more comprehensive analysis on people's expand and salary, as well as their SAT score. Then you do like a multiple regression, the predictors being expand and salary, and respond being the SAT score. But you can't involve like verbal and math, because those two parameters have a way more strong correlation between those two variables and the SAT scores.
Okay.
It's basically
So
not a correlation, it's like the causation, right? You just
causation.
sum up
Yeah.
those two and you get the SAT score. Yeah.
Okay.
So
when I ask,
yep.
so when
Go
I
ahead.
ask, like, check the constant variance assumption for the errors, what do I do? Like,
So
constant.
all those checking is like diagnostic checking. You're gonna look at the residuals, and in regression model, the most important assumptions about the residuals, I guess you intuitively they have constant variance, their mean is 0, they follow a normal distribution. Importantly, they are independent, right? So a perfect regression model is when you complete a regression model and find the residuals, you didn't find any patterns. That means my model is good, because residuals is like what we left up, what's the forecasting errors, right? If the errors have no pattern, that means I cannot reduce it anymore. So that is a good regression analysis. So what you're gonna check the constant variance of the residuals, you just look at, like, you have a 4-in-1 plot, right? There is a residual versus fitted value, and you just see if the variance is the same no matter what is your fitted value. Like, your fitted value is on horizontal axis, it's on x-axis, and then your residuals would be clustered in y-axis. It's in the second graph, I think. It's the residual versus fitted value plot. Right, this one you cannot see it very clearly, but the variance of residuals is like what's the basically it's the highest residuals minus the lowest residuals. In this case, it's all 0, but maybe you just you can look at my previous examples, like I did an example on linear regression, like it's clustering this plot, and no matter what is your fitted value is your forecast, right? It's your prediction. No matter what your fitted value is, your residuals are kind of at the same height. Maybe maybe sometimes I have an error of 0.25, sometimes negative 0.25, but the height is like 0.5, right? And no matter where is your fitted value, you find a similar pattern of the residuals, like they all have a height of between like minus 25 to plus 25, and that is good. But sometimes your residuals are clustering like near 0 when your fitted value is small. However, the regression just diverges, the residual just diverge. Like in the end, when your fitted value equals 1100, maybe your residuals were in between of negative 0.5 to positive 0.5, like it diverges, like it has a higher height. That means the variance is bigger. So basically the residuals, they should have a mean of 0, because that is a default of the least square method, but it has a variance. In this graph, there's no variance at all the residuals are 0, but sometimes they have a higher variance, meaning there's extremely large positive residuals and extremely large negative residuals, and resulting they have a 0 mean. And that's not what we want to see. We want to see the variance is constant no matter where is our fitted value.
Okay. Wait, so on our final exam, like for the regression, will we be just analyzing these graphs then instead of actually calculating them?
It's possible, like, it's possible there would be like 1 or 2 question, small question for you to analyze those graphs. But it's more important to calculate the actual data.
Okay.
You don't like the professor will give you some. They don't give you, for example, 1,000 data points and let you to calculate, right? They will give you something like the like MSE, something the square arrows, the sum of squared arrows. You know what I mean? There you have a lot of formula shit, so you can use those data to calculate the regression model by your hand. You don't have to use a calculator or computer.
Okay. Makes sense.
So in this week's homework, basically you're gonna do, I guess, 4 or 5, I don't know, like 4 single regression analysis. SAT score versus expand, SAT score versus ratio, etc. And then you're gonna look at those different residuals and to see if that is a good model. You can also you have a model summary. What is your R? What is your R squared? Right? Those are all relevant to measure how successful your model performed.
Okay. So instead of like putting all of them into one regression analysis, I just do like
you just do 4. I think it's 4, right? Maybe I check.
There's 4 different data sets.
You just do it separately. You have like expand, that could be a potential parameter. You have ratio, you have salary, you have takers, you have verbal, you have math. So you just do an expand versus total, then you do a ratio versus total, right? You just want to get a common sense of what's the relationship between one parameter and your total SAT score. In reality, there is a very huge problem. I think we will, or I don't know if you have go over that in class, which is how many parameters or which parameters I will choose in my regression model, and that requires an F-test. Because it's common sense, like if I use more parameters, then I will get a smaller residual squared. The sum of residual squared would be minimized by using a lot of parameters, but that would lead to like a problem of like overfitting something. Like there's no pattern at all, but I just assume it has a pattern and I just add some parameters to manually reduce the residuals, which is not correct. A good model is you have as little parameters as possible, like as easy as possible, but also have a pretty high R squared. So there's a trade-off. By having more parameters, it's more complicated, but it reduces the residuals. And otherwise, by using not too much parameters, it's very easy and there's less likely to have an overfitting problem. And that trade-off is determined by the F-test, which is very important. In this case, you don't have to worry about that. You just do the single regression analysis.
Then I do the same thing for the other 4 data sets, right? Like the Prosty data, the Swiss data, and the other, the fourth one.
think you have four. You have another 4 data set.
Yeah. No, there's 4 data sets in total.
4 data set in total. Let's check about the homework.
This is the homework.
Okay, my mistake. My mistake. So I think you're gonna do a multiple regression here, but you look at the parameters. Look at the parameters. SAT score as a response, and expand salary ratio and takers as predictors. So you don't use verbal and math, I think. You don't use verbal and math as predictors. So in your multiple regression model, you only have 4 parameters. You can try it. You can try it now, and you will get something very different.
So expand ratio salary takers. Okay. Oh.
In particular, yeah, you can go to this residual versus fitted value plot. What you find here, I would say it doesn't really have a constant variance, because when your fitted value is like 850 to 900, that's your prediction.
Yeah.
Right? That's your prediction based on those 4 parameters. That's saying I gave you a expand, I gave you a ratio, I gave you a salary, I gave you a takers, and then you're gonna predict what is the total score of that students, right? So when your prediction is between 850 and 900, you will find you have some arrows, right? And those arrows ranges from like 50 to minus 50, or even more, like 50, like 50, I would say 65 or something, from minus 50 to 65, when my prediction is between 850 and 900. However, when your prediction is between like 950 and 1000, your residuals are kind of, it's between 0 and negative 50. Like the arrows are much smaller. So all the arrows, like all the dots on this plot, they have a mean of 0, because that's the mean of all the residuals. However, sometimes it clustering with a high variance, sometimes it clustered with a low variance, and that's actually not very good. It means my prediction is more accurate when my prediction is between 950 to 1000. And actually it makes sense, right? Intuitively it makes sense, because that's more close to like the average of the SAT score. And everybody was just something between 950 and 1000. Whereas it's not very common to score 850 to 900 points. And you have a lot of outliers in that range, so you cannot really accurately predict people's score. So they don't strictly follow constant variance, but it's not bad. It's not bad. You don't see a particular pattern in this plot, right? It's basically chaotic, but you'll find some minus pattern, which is the variance is not really a constant, but not too bad.
Okay.
Yeah, so basically
I
you
just
have
do.
another 4 data set and you do the same thing. You analyze the,
Okay.
right? You know the first plot, right? That's a QQ plot. It's about the
Yeah.
normality test. The second one, you can see if the residuals are constant. The fourth plot, and the third plot, by the way, the third plot is just like a histogram of the residuals. It's not very powerful than the first plot, right? You can still see if that's normally distributed. And from the third plot, you see it's not normally distributed. It's not even symmetric. It's not a
Yeah.
bell curve. It doesn't look like a bell curve at all.
Okay.
And the fourth plot is the residual versus order. So basically, the difference between the second plot and the third plot is the x-axis. In the second plot, the x-axis is your fitted value, which is your prediction,
Yeah.
the prediction of the total SAT score. The fourth plot, the x-axis, is your observation order, which is 1, 2, 3, 4, 5, 6. That is your observation order. You have 50 data at all. You have 50 data in total. And the first one is just in your first line, Alabama. The second
Okay.
data point is Alaska. Maybe, and if some pattern is observed in this plot, it's also not very good. Right, it means maybe some state they are nearby or they're all in the southern part of America and they all they all overperformed than prediction. It's possible, right? And I guess in some state like in New York and Boston, those northwestern states where like I guess the education level is slightly higher than the average, then those states maybe have a cluster of like overperforming, right? But here your 50 observations, they're not sorted by part. They're sorted by the letter A, B, C, D,
Yeah.
right? So it's less likely to have such problems because it adds more randomness.
Okay. Uh, I don't think I have any more questions.
Nice. For the last question, I guess I guess next week I will discuss about the last question. It's more like algebra, algebra, manipulation of the F test,
Okay.
and that I don't think it's really helpful. But one thing, like you and whoever watched the recordings, have to understand is F test. It's very important. It's about how many parameters you're gonna choose, right? In this case, in this homework, we just told you you're gonna use expand, ratio, salary, and takers as parameters. But maybe it's better to just use expand and salary and forget about ratio and takers, right? And how to do that trade-off. There's a F test. I'm not sure if you have go over it, but it's very important, both in your like real life analysis and in the final exam.
Okay. Wait, this is F test, right? ANOVA.
It's kind of different. ANOVA is like 3 or more groups, the t-test for 3 or more groups. Right, so we studied the 2 sample t-test, and the formula is really pretty complicated if you want to calculate the denominator, right? The standard error is you have like s1 squared plus s2 squared, blah blah, and square root, and n1 1 over n1 plus 1 over n2, right? That formula is still very complicated. And the ANOVA is for t-test for 3 or more groups. Because it helps you to find if there's any difference between either two groups. If you're going to do a t-test, like you have A, B, 3, you have 3 groups. If you do t-test, you're going to first test if there is a huge difference between group A and group B, then group B and group C, and lastly group A and group C, right? You're going to do 3 t-tests, and you have the type 1 error rate, which is 5%. That's your alpha. And the more t-tests you do, the more chance you have a type 1 error. So that's why you don't want to do multiple 2-sample t-tests, but rather you do an ANOVA. But that's not required in the exam.
Okay. So how do we do F-test then on?
You need some parameters for F-test. You need some parameters from the regression. I guess it's something like sum of squared errors and the number of parameters, right? In this case, you have 4. That's the number of parameters. Yeah. Like you don't have a direct command on Minitab, but rather you can calculate some key statistics in the regression model, and then that's the something you're gonna plug in the F-test formula. Maybe you didn't go over it already. You still have, like, I don't know, 1 or 2 classes. But that's very important. I just want to say that it's not in this homework, but I will probably go over a question about F-test. In this homework, you already have F-test in the last question, I think.
Yeah.
But that's I'll look at it. Oh, so okay, but the null hypothesis of the last homework is whether the 5 explanatory variables jointly and significantly affect the response variable. So that the null hypothesis is whether my model is good by using 5 explanatory variables, which are the predictors in the language of Minitab. Whether it's good to use 5 predictors, and it's compared with 0 parameters. Right? Is it good to use 5 parameters, or just to say those 5 parameters have no economic interest, have no statistical interest in the regression model? Any other way, the beta for those 5 parameters are all 0. That's the null hypothesis of the last question. But in reality, you don't want to compare 5 versus 0. Maybe there's 2 explanatory variables. In other words, there's 2 parameters, predictors, that you care about. So the decision is whether I use 5 predictors or 2 predictors. And the F-test formula is slightly different. So that adds like 1 more level of difficulty. But in this home assignment, you just need to understand how to test 5 versus 0. Should I use 5 predictors, or I just don't use predictor at all? All the betas are 0.
Okay.